error coefficients. In the previous classes, we have studied about static error coefficients and also how to find the steady state error using static error coefficients. Static error coefficients are Kp, Kv and Ka. So, the static error coefficients does not show the variation of error with time, and the input should be in the standard input such that step input, ramp input or parabolic input. So, this is a drawback of the static error coefficients. So, the dynamic error coefficients eliminates this drawback such that it gives the steady state error as a function of time. By using the dynamic error coefficients, steady state error can be found for any type of input. So, the error signal will have a form of E of t will be equal to R of t into C0 plus R dash of t into C1 plus R double dash of t into C2 by 2 factorial plus R triple dash of t into C3 by 3 factorial plus etc. R n dash of t into Cn by n factorial plus etc. This is the general form of the error signal if we are considering the dynamic error coefficients. So, here C0, C1 etc. up to Cn are the dynamic error coefficients and E of t is the general equation for the error signal. And if we want to find out the steady state error, we know that if we are given the error signal, then we can calculate the steady state error by applying the limit t tends to infinity to the error signal. So, the steady state error will be having the form ESS will be equal to limit t tends to infinity R of t into C0 plus R dash of t into C1 plus R double dash of t into C2 by 2 factorial plus R triple dash of t into C3 by 3 factorial plus etc. This is the equation for steady state error, and that is obtained by applying the limit t tends to infinity to E of t. So, here C0, C1, C2 etc. are the steady dynamic error coefficients, and it is also called generalized error coefficients. So, we want to find out the equation for generalized error coefficients. So, the generalized error coefficients are C1 equal to limit s tends to 0 into f of s, where f of s equal to 1 divided by 1 plus g of s into h of s. So, for doing problems, you will be given the open loop gain g of s and also the feedback gain h of s. If both these quantities are given, then f of s can be easily found out by 1 divided by 1 plus g of s into h of s. So, the dynamic error coefficients will be, the first dynamic error coefficient C0 is obtained by applying a limit s tends to 0 to f of s. And similarly, C1 can be obtained by limit s tends to 0 d by ds of f of s. C2 will be equal to limit s tends to 0 d square by ds square of f of s. That means you should find out the first derivative of f of s and you should apply the limit s tends to 0. And for finding the C2, you should find the second derivative of f of s and you should apply s tends to 0. So, in general, we can write the equation for Cn as Cn will be equal to limit s tends to 0 d raised to n by ds raised to n into f of s. That means you have to find out the nth derivative of f of s and then you can apply the limit s tends to 0. Okay, this is all about the equations for dynamic error coefficients, and you know that once you get the value of C0, C1, you can apply the value of C0, C1 to this equation. Okay, where here in this equation you see that there is R of t is the input signal, that is input signal, and its Laplace transform will be R of s, and R dash of t is the first derivative of input signal, R double dash of t is the second derivative of input signal. Okay, once you got these two values, that is C0 R of t, C1 R dash of t, you can find the steady state error ESS by applying those values to this equation. Okay, so there is a correlation between the static error coefficients and dynamic error coefficients. You know that static error coefficients are Kp, Kv and Ka, and that are related to the dynamic error coefficients C0, C1 and C2 by the equation C0 will be equal to 1 divided by 1 plus Kp, C1 will be equal to 1 divided by Kv and C2 will be equal to 1 divided by Ka. See, we know the equation for C0 as C0 will be equal to limit s tends to 0 f of s. We know that f of s is equal to 1 divided by 1 plus g of s into h of s. And if we are applying this limit s tends to 0 to the quantity g of s into h of s alone, then we will get like this. So, this term will be equal to Kp, so that will be equal to 1 divided by 1 plus Kp. Similarly, we can derive the equation for equation for C1 equal to 1 by Kv, that you should do yourself. First take the equation for C1, that means C1 will be equal to limited s tends to 0 d by ds of f of s, and then apply the limit s tends to 0 to f dash of s. First of all, you should find the f dash of s and you will get this equation. Okay. So remember the relationship between these three quantities, that is C0 related to Kp by 1 by 1 plus Kp, C1 related to Kv by 1 by Kv, C2 related to Ka by 1 by Ka. Okay. Next we can do a problem. So for a unity feedback control system, the open loop transfer function g of s equal to 10 into s plus 2 by s square into s plus 1. Find the position, velocity and acceleration error constant. Find the steady state error when the input is r of s, where r of s is equal to 3 by s plus minus 2 by s square plus 1 by 3s cube. This is the question. So in the question, open loop transfer function is given, that is g of s is given. It is given that it is a unity feedback system, that means h of s equal to 1. So you are asked to find Ka, Kv and Kp. So for finding out that, you should know the equation for Kp, Kv and Ka. That means Kp, Kv and Ka are static error coefficients. So first solution is to find the static error coefficients. Position error constant is Kp. Kp is given by the equation limit s tends to 0 g of s into h of s. Similarly, Kv has the equation limit s tends to 0 s into g of s into h of s. Acceleration error constant has the equation limit s tends to 0 s square into g of s into h of s. Here g of s is given and h of s is 1. You can directly apply the values of g of s and h of s and you can solve for this equation. Okay. Here is the steps, and once you are applying the limit s tends to 0, you will get the value infinity. Here for Kv, you can substitute for g of s and h of s and s. So you will get the equation like this, and if you are applying the limit s tends to 0, then that will be equal to infinity. See, here in the denominator there is an s term. Once you are giving s to 0, then 1 by 0 will have a form of infinity. That is why we are getting these two values as infinity. Similarly, acceleration error constant have an equation like this, s square into g of s into h of s. If you are applying the limit s tends to 0, you will get the value like this, 20. Okay. In the next step, you want to find out the steady state error when the input is r of s. That means here the input is not in the form of standard input. That means it is not in the form of step input or ramp input or in the form of parabolic input. So we want to find out the steady state error by using the dynamic error coefficients. Since the input is not in the form of a standard signal, so first we should find the dynamic error coefficients such as C0, C1, C2, and then we can write the equation for error signal, and then we can find the steady state error. Okay. So to find the steady state error, for the non-standard input, the generalized error coefficients will give the standard error signal, and the error signal E of t will have the form r of t into C0 plus r dash of t into C1 plus r double dash of t into C2 by 2 factorial plus etc. This is the general form of error signal. In this case, you should find C0, C1, C2. Also find r dash, r of t, r dash of t, r double dash of t, r n dash of t. Here you are given by r of s, that is the input signal. Laplace transform of input signal is given, that is given. So first, in order to find r of t, you should find the inverse Laplace transform of this r of s. So inverse Laplace transform of r of t will have a form like this. You should know to find the inverse Laplace transform. Inverse Laplace transform of 1 by s is 1. Inverse Laplace transform 1 by s square is t square by 2 factorial. Inverse Laplace transform 1 by s cube is 1 by s cube is equal to t cube by, inverse Laplace transform 1 by s square is t, and 1 by Laplace transform 1 by s cube is t square by 2 factorial. So you should know the equations for inverse Laplace transform, then only you can find the solution. So we will get the r of t signal as 1 by 3. See, here first form has a value 3, 1 by 3 minus t square 3 minus 2 into t square by 2 factorial plus 1 by 3 into t square by 3 factorial, t square by 2 factorial. So you got the form like this, that is 1 by 3 minus 2t plus 1 by 3 into t square by 2 factorial. Here there is a mistake, it is not 1 by 3, it is 3, okay? There is a mistake in the textbook. So that is, here it is given that 1 by 3, it is not 1 by 3, it is 3, okay? You should replace 1 by 3 by 3. 3 minus 2t plus 1 by 3 into t square by 2 factorial. So here instead of 1 by 3 you should write 3, okay? 3 minus 2t plus t square by 6. That is the actual equation for r of t. So next you should find r dash of t, r double dash of t, r triple dash of t, etc. So first r dash of t. R dash of t is obtained by the first derivative of r of t. Take the first derivative r of t, that is simple mathematics, you can write it. And r double dash of t is the second derivative of r of t. Write the second derivative r of t, and r triple dash of t is the third derivative r of t, and you will get the equations like this. Okay. So once you get the first derivative r of t, you can find that a triple dash of t is equal to 0, and so after that the derivative will be equal to 0. So we need to find only r of t, r dash of t, r double dash of t, and r double dash of t. So we need to find c0, c1 and c2 only, okay? So the generalized error constants will have an equation c0 equal to limit s tends to 0 f of s, c1 will be equal to limit s tends to 0 d by ds of f of s, c2 will be equal to limit s tends to 0 d square by ds square of f of s. See, first you should find the first derivative of r of t, r double dash of t, r triple dash of t, and when it becomes 0, then you need not find out the error quotients corresponding to that term, okay? So here 2 terms have the values, 3 terms have the values such that r of t has a value, r dash of t has a value, r double dash of t has a value. So you need to find only c0, c1 and c2, okay? So write the equation for c0, c1 and c2, and here you want to find out f of s, where f of s is equal to 1 by 1 plus g of s into h of s. This is equation for f of s, and in that h of s is equal to 1. So you can substitute the value for g of s and you can find the f of s like this, okay? That is simple mathematical procedure, and c0 is obtained by applying the limit s tends to 0. So you will get the c0 value is equal to 0. When you are applying the c1 equation is limit s tends to 0 d by ds of f of s. First find out the first derivative of f of s and apply limit s tends to 0. So you will get the value like this, 0. c1 will be equal to 0. Next c2 has the equation like this. So substitute the value of f of s and find the second derivative, and you will get the, and apply limit s tends to 0. So you will get the value 1 by 10. So c0 and c1, c2 value you got. Here c1 value is equal to 0. So that term will not be in the equation for error signal. So error signal e of t will be equal to r of t into c0 plus r dash of t into c1 plus r double dash of t into c2 by 2 factorial. This is our error signal equation. In this c1 term is equal to 0. See, c1 term is 0, so that will not be appear in the answer. So if you are substituting the values of c0 and c2 and r of t and r double dash of t, you will get the equation like this, okay? That is, the signal will be equal to 1 by 60 is the value of error signal. That means e of t is a constant value, and steady state error can be obtained by applying the limit t tends to infinity e of t. Here there is no t term, so limit t tends to infinity 1 by 60 will be equal to 1 by 60. So that is the steady state error, okay? Here you should know the procedure to find out the error signal, and here the input is not in the standard form, so you should find out the dynamic error coefficients, and you should know the equations for dynamic error coefficients, and you should know the equations for f of s. Then only you can find out the steady state error, okay? That is the procedure. And there is another method, simple method. Here we want to find out first derivative, second derivative, and it is a lengthy procedure. There is a simple method to find out the solution. You can either either use this method or first method, okay? Second method is that here the error signal in S domain will have a form E of S is equal to R of S divided by 1 plus G of S into H of S, and this equation you should by heart, and it is used in the case of static error coefficients. Okay, U of S error signal will be equal to R of S divided by 1 plus G of S into H of S, and here R of S will have a form like this, that is given in the question, and G of S is also given in the question, and H of S is given in the question, and you can substitute these values, so R of S, G of S and H of S. So this is the equation by substituting R of S, G of S and H of S, and in this this is the equation for E of S, and in order to find out the error signal E of t, you should represent it in a generalized manner, and here in the first term it is taking 3 by s outside and also taking 2 by s square outside, and in the third term 1 by 3 s cube is taken outside. Here you can see by rearranging this equation you will get this term in the denominator side will be coming to the upper side, so that is shown here, and the denominator will be this term. Okay, so the numerator will have this term also, and so we are separating each of these terms, so we will get this equation of E of S, and the steady state error has a equation ESS will be equal to limit t tends to infinity E of t, and this is by applying the final value theorem, this can be obtained by applying limit s tends to 0 s into E of S. Okay, so there is no need to find out the inverse Laplace transform. We can find the steady state error by using this equation, that is limit t tends to infinity E of t will be equal to limit s tends to 0 s into E of S. So steady state error can be obtained by ESS will be equal to limit s tends to 0 s into E of S is this term. Okay, E of S can be substituted here, so E of S will be substituting here, and we can simply apply limit s tends to 0, so we will get the solution 1 by 60. So this is an easy method. You can either do the first method or second method, that is your choice, but it will if you are using the second method it will save the time. Okay, this is all about dynamic error coefficients. In the textbook there are a lot of problems, you can do the problems and you will get familiarized with the concept. Okay.